For the honor to actually start this conference. I was in a big dilemma because I submitted this abstract and I was not sure what I should actually speak about. But in the end, I decided nevertheless to speak about quantum simulations with cold Rydberg atoms. Now, this was work done mainly in collaboration with Peter Soller, and most of the calculations actually did Hendrik Weimar, my PhD student, and a lot of discussions also went with Tilman Pfau and Robert Löh. Now, I don't think I really need to introduce Rydberg atoms to you. Now, everybody knows that the Rydberg atom is a highly excited electronic state of an atom, and we have this. The graphics doesn't seem to be very good. Let me shortly try. Oh. Okay. Yeah. Okay. So. And we have very well selective Rydberg states which we can excite via laser excitations. And due to the defect theory, we can really select S and P wave stage which can selectively excite it. And due to the large dipole moment, this gives actually rise to very strong Rydberg-Rydberg interactions. And this gives rise to the well-known blockade phenomena, which means that actually if we are looking, for example, at the 43S state in rubidium, then we get a very strong van der Waals repulsion, which is shown here. We have the van der Waals coefficient scales like n to the power of 11. And therefore, if we try to excite two atoms into the excited state, it's actually possible as a function of the distance to excite one atom. But as soon as we try to excite the second atom, it's shifted out of resonance, and therefore the phenomena is blocked. And this gives rise to the so-called blockade phenomena, which has give rise to a lot of experimental work and also theoretical work. Now, we have studied this regime and proposed that there is actually some quantum critical behavior. And this is somehow my dilemma. I wasn't sure whether you are more interested in actually these results or more in actually the Rydberg simulations. And therefore, I decided actually to drop out the quantum critical behavior. Please ask me afterwards if you're interested in this. Also, it will fit much nicer into this session. But I will actually talk more about some perspective and future possible applications of Rydberg atoms. And for that, I will actually, in the first part, use this blockade phenomena to propose a mesoscopic Rydberg gate, and then try to tell you that we can actually use Rydberg atoms, even if we are not able to really build a perfect quantum computer. If you are just interested in simulating some systems, there is actually much lower restrictions which allow us to simulate interesting many-body physics. And then, therefore, I will make a proposal how we can actually use this many-body Rydberg gate for a quantum simulator. Now, due to the blockade phenomena, there was this very seminal work by Peter Soller and Ignacio Cirac and Michel Lukin, which proposed that actually the blockade phenomena can be used to build up a 2-qubit gate. And there has been recently these very excellent experimental results by the group by Marc Safman and by Philippe Grangier and Antoine Broadway, where they actually finally realized this 2-qubit gate and showed the coherent excitations and pi pulses on single atoms into the Rydberg state. But as soon as one achieves what theoreticians have proposed, one can ask, can we actually achieve much more? And one interesting question is, can we actually achieve a gate which is not only a 2-qubit gate, but it's actually a gate which controls automatically many atoms, which means that it's a single gate, but it acts on many atoms and implements a C0 in power of n, which means it's a C0 gate, but the control atom controls many ensemble atoms. Let me explain this in more detail, what we are actually interested in, and what I would like to convince you that with Rydberg atoms can be very easily achieved. So we would like to make a many-body gate where we have one control atom. Is there actually a better laser pointer? Or okay. Or Okay, so where we have one control atom, so this control atom has two states. It can be in state 0 or in state 1. And there are many ensemble atoms which have two states. They can be in state A or in state B. And the idea is, depending on the position of the control atom, we can flip all the ensemble atoms. So the idea is, if the control atom is in state 0, nothing happens to all the ensemble atoms. However, if the control atom is in state 1, all the ensemble atoms should make a transition from state A into state B. And that in a coherent way, that it is really a unitary gate, which can also invert it, and vice versa. Now, how can one achieve this gate very easily? And that I will illustrate in this figure here. So what we want first to achieve is the gate operation that the control atom is in a state 0. That means that nothing should happen to all the ensemble atoms. And the idea is to use the EIT condition, which actually blocks a Raman transition. And this is illustrated here. So we are with the control atom in state 0. We apply a pi pulse which should excite into Rydberg state. But as we are in state 0, nothing happens to the control atom. Now for the ensemble atoms, we want to make a Raman transition from state A to B, but we want to make it far off resonant. But if you have a very strong coupling laser, which actually establishes the EIT condition, we know that the P level becomes dark. So the ensemble atom doesn't see at all the light coming from the Raman transition due to the EIT condition with the strong coupling to the Rydberg state. Therefore, in these situations, we shine in lasers, but nothing happens to the system. So here we do not excite because the control atom is in a state which doesn't couple to the Rydberg state. Here we don't make a Raman transition because we are exactly on the EIT condition, and therefore the atom is dark to the Raman lasers. Now the opposite happens if you are, please excuse, if you are in state 1, I have to try it again. Here. If you are in state 1, we would like to make the transition. So the control atom is in state 1, it gets excited into the Rydberg state, and now we see, due to the Rydberg-Rydberg interaction, the EIT condition is violated. So now the two-photon resonance is no longer satisfied, and therefore actually the atoms here see the Raman transition and they make a transfer. Now the nice thing about this setup, this very simple setup, is that it is completely independent on the exact position of the particles. The only condition which has to be satisfied is that the EIT condition is violated enough such that the Raman transfer takes place. So the Rydberg atom interactions and this Rydberg state should be strong. But the nice thing is that there aren't at any time actually two atoms in a Rydberg state. So during all the process, only the one atom is in a Rydberg state, and all the other atoms are safely in the ground state and far detuned from the P state. Now, if one inserts the numbers and tries to see whether it really can work out, there are several conditions one has to satisfy. Now, the shortest time scale, or the longest time scale in the problem, is actually the radiative decay of the control atom from the Rydberg state. And therefore, the full gate has to be performed faster than this decay process. Then there is a condition which tells us whether we are able to block the EIT condition or not. And then there is the remaining condition, which is the interaction between the Rydberg atom and between the two Rydberg atoms, the control and the ensemble atoms. And it actually turns out that with a very high fidelity of 99%, one can achieve the gate with the following numbers here, which are challenging for experimentalists, but within range. And so, the full limitations is just that we need very strong Rydberg interactions divided by the radiative decay. And we know that the higher the n quantum number of the Rydberg state, the longer the lifetime of the system, and the stronger the interactions, and therefore this quantity can be of several orders of magnitude. Now, if one is very careful, one immediately can claim that actually we cheated a little bit, because I didn't tell you actually that so far I ignored the influence of the interactions between the ensemble atoms. I told you that there is an interactions between a control and the ensemble atom, but I ignored the influence between different ensemble atoms. And the question was, does this actually spoil the scheme immediately, or what is the role of these interactions? Now, it actually turned out, which was very surprising for us, that Markus Müller ran the simulations for two ensemble atoms, and here are the results for the gate fidelity, and it actually turned out for increasing interaction between the ensemble atoms, the fidelity saturated at the constant level. And this was very surprising that actually we were fearing that actually the ensemble interactions will spoil the gate, but it actually turns out that independent on the strength of the ensemble interactions, the gate works nevertheless. One just has to increase the coupling laser for the EIT condition to recover the high fidelity of the gate. Now, how can one actually understand that this really works? The simple explanation is, so which part of the gate actually fails is if the control atom is in state 0 and nothing should happen. That's the dangerous part, because the interactions between the ensemble and ensemble atoms can violate the EIT condition. While if we want to make a transfer, the interactions doesn't play a role, because it just shifts the system further out of resonance with the EIT laser, and therefore the transfer takes place nevertheless. So one can ask, what does the role of the interactions in an ensemble for the blocking scheme? And therefore, we have to note that actually for making a transfer from one atom from state A to state B, we have to excite it once into the P state for a single Raman transfer. But if we want to excite it to a P state, we have to violate. So this condition is always, this coupling is never present due to the EIT condition, because here we only have one Rydberg atom excited. And so it's a collective state with only one Rydberg state, and therefore the ensemble interactions doesn't yet take place. And therefore the first step in the transfer is already blocked, and therefore the blocking takes place nevertheless, although we have the interactions between the ensemble atoms. Okay, so that's the basic idea, that there is actually a unique tool, and this tool sounds a little bit like a miracle, because usually it's always possible to build up a many-body gate out of 2 qubits gates, but this gate here one cannot build up, because it doesn't matter how many ensemble atoms we have in the system. The gate works whether we have 3 ensemble atoms or 2 ensemble atoms, and the gate works independent on the position of the particles. And that is a very unique and novel feature which we have here. And this allows, for example, to make beam splitter experiments where we can study the wave function of a system by making a beam splitter, entangle the control atom with the system, undergo the dynamics on the ensemble atoms, re-entangle it again, and measure afterwards the probability to be in a control atom. And with this method, one can actually measure wave functions during different evolution of the system. If one is interested in a more classical applications of the gate, one can also use it as a Rydberg enhancer or amplifier. So we can see that if you have one atom which is in a Rydberg state, we can make a transfer for all the surrounding atoms from one internal state to another, and therefore it enhances the signal around the Rydberg atom. So it is a very useful tool to use it as an amplifier in situ to transfer around the Rydberg atoms many ensemble atoms into different internal states, and therefore then detect just atoms instead of a single Rydberg atom. But what I'm interested in the following is actually more, if you have a pure n-body interaction, then one can always make a many-body gate with it. And therefore the questions, here we have a many-body gate, which is a control C0 for many ensemble atoms. can we actually reverse the process and use this for the quantum simulations of n-body interactions? This will lead me to my second part of my talk, where I would like to propose you that actually Rydberg atoms are a very useful tool for building a quantum simulator. Now, what is a quantum simulator? It was first proposed by Feynman in 1982 that actually, if you're interested in simulating a quantum system on a computer, we should actually use another quantum system to simulate the interesting quantum system, because only a quantum system has the large Hilbert space which is required for simulating actually another quantum system. And this has recently led to the proposal to use cold atoms, for example, in an optical lattice to simulate the Hubbard model, which is expected to play an important role for the high TC superconductivity. Now, why do we actually need a quantum simulator? And why can we not do it on a classical computer? And the problem is that, on one hand, the Hilbert space grows exponentially with the number of atoms in a system. That means in one dimension, we know we can do density matrix renormalization group, DMRG methods, but the limitations is the large size of the Hilbert space. So we can make efficient calculations, but the systems cannot be too large. If you want to do quantum Monte Carlo calculations, we have the problem of the sign problem, which doesn't allow us to study fermionic systems. And therefore, if you have a model like the fermionic Hubbard model, there are nowadays no tools which allow us to simulate these systems on a classical computer. And therefore, the idea is to implement the Hubbard model in a different system, which is a different system of atoms, for example, atoms in an optical lattice, perform experiments on this system, and therefore get information about the Hamiltonian of the fermionic Hubbard model, and in the end make conclusions about the high TC superconductivity. Now, that's one purpose of quantum simulations, but there's another part which is maybe more fundamental. It also allows for search of novel matters. There are many proposals out there that actually possible phases of matter involve very exotic states such as spin liquids and topological phases, but nowadays nobody knows how often appear these phases in physics, or are they at all possible? And the quantum simulator would help us to ask these questions. Now, in the following, I will be interested in actually build up a quantum simulation for a Hamiltonian which involves many-body interactions. And the prime example in condensed matter physics is nowadays the so-called toric code, which has the following interactions. It exists of spins sitting on the links of a lattice, and we have the many-body interactions that on each blockade the AP term is the product of 4 sigma Pauli X operators. So it involves it's a 4-body interactions, as each term involves 4 spin operators, and on each side we have a product of 4 sigma Z operators, which is the product of these 4 operators times sigma Z. And this toric code has attracted a lot of interest because it's one of the simplest models, which is one of these exotic phases like a spin liquid and has anionic excitations. So it's an exactly solvable model, but we know that actually all these interesting models require such high many-body interaction terms. And nowadays, there are only limited tools to actually implement such Hamiltonians. Now, in the following, I would like to show you that if we want to make a quantum simulation, it's actually important that we not only implement the Hamiltonian, but that we also implement a dissipative term which allows the cooling of the system. And in my talk, I will focus on a dissipative term which is given by a Liouvillein in the Limblad form, where we have the jump operator. So ρ is the density matrix of the system, and we want to couple the system via jump operators such that the system reduces to the Limblad form. Now, why is this interesting? I said that we actually want to use these jump operators to cool the system, and one can immediately see that there's a very trivial solution to the master equation, namely if the jump operator applied on a state vanishes for all jump operators, then there is a trivial stationary state which is the pure state of this state D. And I would like to call this a dark state because it vanishes with all coupling to the reservoir. Now that tells us that as soon as we have dissipation and we have this condition that all jump operators on an interesting state D vanishes, then you have a very trivial solution to the master equation, namely the pure state, which is the stationary state of the system. Now one can reverse it and ask, can we actually engineer jump operators in such a way that this pure state is the ground state of our Hamiltonian we are interested in simulating? And can we design the jump operators in such a way that under time evolution the system cools itself into the ground state of the many-body system? And to illustrate this, one can easily see in an above example of the toric code how this works. So here's again the toric code with our four-body interactions on a placket and the four-body interactions on each side. Now the ground state is uniquely determined that each of these interactions applied on the ground state has eigenvalue 1, and the Hamiltonian is minus the sum over all these interaction terms. So we see that these operators commute each with each other. So they are all, so the ground state is an eigenstate of all of these interaction terms, and therefore this the state satisfying this condition is the unique ground state of the system. Unique, I have to be careful for specialists, as it is a topological phase. There's a ground state degeneracy which depends on the boundary conditions on the system. So if there is a hole in a system, the ground state will scale with the number of holes. Will scale with n to the power the number of holes in a system. And there are two types of excitations. On one hand, one can violate one of these interaction terms, which one then calls a magnetic excitation, or one can violate the constraint, the interaction term on the side, which then is denoted by a charge excitation. And now one can see that actually the following jump operator will cool the system uniquely into the ground state of the toric code. And the idea is, so we have here a magnetic excitation, so this which is excited. Now we can apply the jump operator, study the time evolution. The time evolution corresponds to applying the jump operator onto the system. That means that we measure whether there is an excitation on this side. If we are in an eigenstate 1, the ground state vanishes and nothing happens. If we are in eigenstate -1, this term doesn't vanish, and then we apply a correction term on one of the surrounding atoms. That means that if you have an excitation here, one of this system is flipped, and as a consequence, the excitations diffuses through the system. Now if you apply the process again, this excitation will diffuse again, but as soon as we have two excitations of the same kind on the same side, they annihilate each other and the system goes into the ground state. And so that tells us really that the system in this way is cooled into the ground state by the diffusion of these excitations of the system. And now the question is, so this is some interest in condensed matter to actually try to build up a quantum simulations. And the question is, what will be an optimal system for implementing such many-body interactions and such many-body spin interactions? And my proposal is actually that the Rydberg atoms are a very suitable tool for this implementation using the previously proposed many-body Rydberg gate. And the idea is that actually we do not want to really simulate a Hamiltonian in a system, but we would like to just make a digital quantum simulation which tells us that at some time Tn, the system we are interested in is described by a density matrix ρ of Tn, And during a single time step, we want to map the density matrix onto a new density matrix in such a way that it actually simulates the time evolution with our master equation. So for the coherent part, we would like to have the coherent time evolution of our density matrix. If you have a dissipative term, we would like to simulate it in a limb platform. Now that tells us that this digital way, this mapping, can be achieved by applying unitary gates onto the system. And therefore, somehow the system cannot, there will be a Hamiltonian where the system evolves in time too, but we write on top of this evolution a digital one, which is digital because it's continuous time steps which are discretized, and we force the system within each time step to evolve exactly under the evolution we wish it to enforce. And the only restriction is that actually the time scales should be very fast compared to the internal dynamics of the system. And if you compare a conventional simulations with a digital quantum simulation, so in a conventional method, we try to implement the Hamiltonian and try to set up the system in thermodynamic equilibrium. The problem is that if you have high many-body interactions, these terms appear as high order in perturbation theory and are usually extremely small and very hard to study experimentally. And the second problem is that we must engineer a thermal reservoir, or it's only possible to have adiabatic evolutions to prepare the system in the ground state. If you have a digital time evolution, we have the density matrix which is mapped onto a new density matrix within each time step. The energy scales are just determined by the time scale necessary during each time step. And in addition, we can use the adiabatic evolution. And now comes the important part, which is probably interesting for all the people here, which is how can we actually achieve this with Rydberg atoms? And the idea is the following. So we place Rydberg atoms into a large spacing optical lattice where the spacing is of the order of 1 to 5 micrometers. So we have two different types of atoms or two different internal states. We have the blue part, which corresponds to our ensemble atoms, which are the atoms of the system we would like to simulate. And then we have, in addition, the red atoms, which are the control atoms which are necessary for implementing the time evolution. Now, as we are in a large lattice, optical lattice, we can have single-sided addressability, like was demonstrated by the experiments by Marc Safman and Philippe Grangier. So we can address each atom individually. And the level structure is as it was required for the many-body gate, that the blue atoms have two internal states with a coupling laser establishing the EIT condition, and we have the control atoms which has two internal states which can be excited into a Rydberg state, and we have a cycling, we can optically pump one state into the initial state 0. Now the advantage is that what has already been demonstrated by the experiments by Marc Safman and Philippe Grangier is that we can really make such large optical lattices. We have single-site addressability and can very easily apply single gates on the system. The 2-qubit gate has recently been demonstrated. The fidelities are not yet very, for theoreticians, not yet extremely high, but as the experiments are very young, one can be very promising that one can improve it. And if one compares the timescale which are necessary for the implementations, they are of the order of microseconds, and therefore the energy scales which can be simulated are much larger than usual lattice experiments and usual energy scales which can appear with cold atoms in optical lattices. And certainly the biggest problem is that so far these experiments were performed on 2 atoms. The goal would be to actually have up to 100 to 1,000 atoms, while at the moment it's only a scalability to maybe 3 or 4 atoms is possible with the current setups. However, to go to 100 or 1,000 atoms, one really needs large optical lattices, like in experiment by David Weiss or by the experiment by Markus Greiner with single-site addressability. So how I'm doing with time? Okay. So there are now two parts. There is now the questions, how can we actually implement this Hamiltonian, and how do we, which gates do we actually have to apply for the simulation? And again, I will focus on a single placket and tell you how the setup works for only 4 ensemble atoms with 1 control atom. And the idea is that we have a sequence of 3 different steps, okay, actually 4. So we have first, so what we want to do is the control qubit should go from state 0 into state 0, so it should not participate in the dynamics of the system. The spin system should evolve under the desired time evolution, which is either coherent or can be dissipative. And to achieve it, we first entangle the ensemble atoms with the control atom. Then a manipulation of the control atom takes place. Afterwards, the entanglement is reversed, and in the end, an optical pumping is necessary for the dissipative step. Now let me tell you this in detail, how it actually works. So the first part with operation G is actually our many-body gate in control with a pi/2 rotation. And what this operation does, so we have these 4-body interactions, which has which has many eigenvalues which has many eigenstates with eigenvalue plus or minus 1. So lambda denotes the eigenfunctions, plus or minus 1 the eigenvalues. So if you are in an eigenfunctions with eigenvalue plus, then nothing happens to the control atom under this gate operation G. But if you are in an eigenstate minus 1, this information is mapped onto the control atoms. That means after this operation G, we know in which eigenvalue is the system with respect to this operator. And this is directly achieved by our many-body gate I've proposed earlier. Now once the information is written onto the control atom, we can make a single phase rotations onto the control atom, reverse it, and what it corresponds to is that a controlled phase, a phase operation onto the control atom in an intermediate time step actually corresponds to a phase onto the many-body operator, which is exactly the desired operation. On the other hand, if we measure the eigenvalue here, so if we map the information onto the control atom, whether we are in plus or minus eigenvalue, we can also now make a controlled spin flip and correct this process. So if we make a controlled gate in between, the system exactly reduces to the dissipative time evolution. Now, there are some technical aspects that actually the system has to be scalable if we want to really make a large quantum simulation. And indeed, as we have only local operations, we can apply many operations in parallel, and therefore the time scale for each time step doesn't scale with the system size, but is actually independent. And if we would like to make the toric code, I've shown you exactly previously how the system would like to look like. So we need these 4 atoms. We have the control atoms here, and on the sides, each one mediating 1 interactions. This allows us for an efficient quantum simulation of the toric code. But there are also much more exotic and interesting phases. One is, for example, in a lattice gauge theory, which is also not possible to simulate numerically, and this method will actually allow to really cool into the ground state of a spin liquid phase and allow to study such exotic phases which properties are very similar to our normal quantum electrodynamics. So such lattice gauge theory is a ground state of a system which has the same properties as we are used with light. So there is a photonic excitations with 2 polarizabilities in a system. There is a gauge invariance, and there are charged excitations which are interacting via a Coulomb interaction. And with that, I came to the conclusion, and I would like to repeat that I've tried to convince you that Rydberg atoms are a very useful tool for a many-body gate, And it has applications to build up quantum simulator, even if you don't have perfect fidelities for building a universal quantum computer. There are a lot of applications one can do with Rydberg atoms before one reaches these universal quantum computers. Thank you for your attention.
Behind, but if there are a couple of quick questions, Mark?
On the many body gate, you talked about a high fidelity, I think 0.99 for 2 ensemble atoms.
Yes.
What can you say about the scaling of the fidelity
With the other?
atoms?
Yes, the simplest. Okay. Let me go back. So there's this simple argument that actually you see that for increasing coupling laser, one gains back the fidelity. So the question is, how strong can we couple the P level to the Rydberg state? Now, if we have many ensemble atoms, we have to be stronger than the collective Rabi frequency for the Raman transition. So that means that actually the coupling laser times the number of ensemble atoms, square root of it, should be much smaller than 1. And this tells you actually the scaling which you have to beat. So if you have a 2 ensemble atoms fidelity which is given, if you want to have now a n-body atom fidelity, you should increase your coupling laser by square root n to get the same fidelity back. So that is a simple estimate for it.
So the fidelity goes like 1 over n or n squared. But
Okay, the fidelity goes worse, but yeah, so if you want to keep the same fidelity, you have to increase the coupling laser a lot. Now, that tells you that actually if you want to make it as a classical gate, you're lost because you don't have such a high coupling laser. But it doesn't really matter because in a classical sense, if you do it and you don't have a high gate fidelity, it just tells you if there is no Rydberg atom, you do nothing. But if there is a Rydberg atom, you transfer 50% of the atoms into the ground state, which means the fidelity is extremely poor, but as a classical gate, it still works perfectly to enhance the signal.
So I just have a quick question about your last part of the talk. So I'm wondering, to what extent is your method really allows for quantum simulations in particular? So it's very clear that you told us that you can prepare a well-defined state, for example, a ground state of this toric, but all of this kind of interesting phases are really not characterized by the states, but they are characterized by things like excitations. So for example, it's not clear to me that these excitations in your system will actually be anyone's, because there's no Hamiltonian, right?
There is the Hamiltonian because, so there are 2 parts. You have the coherent time evolution, and the other Hamiltonian is inside. And so you have the dissipative. Exactly.
And then
You need both. So that the dissipative term is for preparation, and then you evolve it with the Hamiltonian. Because you have local addressability, you can create an excitation, study how it evolves under the Hamiltonian, and study the system. Yes, no, but it's actually both necessary. The ground state cooling doesn't give the information.
I wonder if Francis could ask his question during the break.
Sure. The one thing that I'm always curious about is how does the dissipative part scale? So you said let's do 10,000 atoms. Does the dissipative part then kind of bite you, or is that irrelevant?
Let me try to understand.
So
In
you
a
have-
quantum simulation.
So you have radiative decay from the 5P is a dissipative thing. Is that going to affect the final result?
For the quantum simulation,
Yeah.
it will give you an error. I mean, there are gate imperfections which are also decay, radiative decay from the Rydberg state. But the main idea is that the Rydberg state isn't excited for a long time. It's not only shortly for the gate. During that time scale, so if it happens that it decays, it goes back into some state. And during some time step, you write the wrong phase onto the system. That will give rise to a perturbation through your Hamiltonian. So the answer is essentially that imperfections or radiative decay give you corrections to your Hamiltonian, but as long as your ground state is really correct, that your one interested in ground state properties, then small perturbations don't play a role. So the answer is it should not.
Let's thank the speaker.
Okay.